Hello everyone, we're continuing our topic of electrochemistry and we are picking up on this video with potential free energy and equilibrium. So we've learned in the past that by definition the standard free energy change is associated with the work that a system can perform. And when it comes to cell potentials, the work associated with transferring electrons is going to be determined by the total amount of charge in coulombs transferred and the cell potential. And so we get this equation that relates the standard free energy to the standard cell potential, where N is the number of moles of electrons transferred, and so that's going to come from our balanced redox reactions. It's the number of electrons that you cancel out on either side of the equation, and we'll see some examples of that. F is Faraday's constant, so that is roughly 96,500 coulombs per mole. You can get a more exact value. I think it is 96,485 if you need more significant figures, but for this course, this will be enough. And the standard cell potential, of course, we've seen is denoted by that degree symbol next to the E. So from the past, we've learned that spontaneous reactions are represented by a negative delta G value, and we also know that spontaneous reactions are represented by positive standard cell potentials. And so we can see that relation, right, with that negative sign between having a positive cell potential here, and then that would give you a negative delta G value. Okay, and then remember on our topics in thermodynamics and equilibrium, we were able to relate the standard cell or the standard free energy to the equilibrium constant K, right? That was equal to negative RT times the natural log of K. Of course, where R represents the gas constant and T represents the temperature in Kelvin. So we can now relate that equation to our negative NF standard E, right? So that we can now relate the equilibrium constant to the standard cell potential. And the way we do that, we can rearrange the equation. And of course, you get the standard cell potential equals RT over NF times the natural log of the equilibrium constant. And so this diagram here to the right just kind of gives you all the three equations in order to relate those three different types of variables, K, delta G, and your E, standard cell potential. So from that equation, where we relate the cell potential and the equilibrium constant, we can see that if we have a very large standard cell potential, of course that means that we need to have a very large K value, and in order to have a very large K value, remember that that's always the products over reactants, of course, raised to the power based on their coefficients. And so if we have a very large standard cell potential, we're going to have a very large K, which means we have more products than reactants. And so that reaction is going towards completion, where our reactants are mostly being converted to products. Okay, so let's try an example where we try to relate all three of these variables. What is the standard free energy change and the equilibrium constant for the following reaction at room temperature? And is this reaction spontaneous? Okay, so we are first going to have to determine what is the standard cell potential, right? We need that before we can use the standard cell potential to find the other two variables. And so our first step is to determine what is E cell. And remember in previous sections on this topic, we learned that that is equal to the standard potential for the cathode minus the cell potential of the anode. And we also have to remember that the cathode is where reduction happens, right? And the anode is where oxidation is happening. Okay, so in order to use this equation, we first have to determine what is being reduced and what is being oxidized. Okay, and so you've got these two half reactions. If we split them up, you've got those two copper 2+ ions that are going to copper with a single positive charge, and so that charge is being reduced, right? You're going from a 2+ down to just a +1, and so that would be your reduction reaction, and that means that tin must be oxidized, right? So we're going from a neutral tin atom to an ionized tin 2+. Okay, and so that would be your oxidation. And so now we need those reduction potential values that you get from that table. You can find this in your textbook. That's where I've pulled this out from. But make sure that you are using the right equation. So we need that copper 2+ and +1, and so you'll find that here, right, going from a copper 2+ to a copper +1. And then for tin, of course, remember that all of the equations in the table, those are all reductions. And so you have to look at it in reverse for that oxidation reaction and find you've got the tin 2+ going to a neutral tin. And so those are the two half reactions. Those are the two standard potentials that we need. And then we're going to take the cathode, and remember the cathode is where reduction happens, so that is your copper reaction, and we'll take that value of a 0.153, and then minus the anode, which is a negative 0.1375. Okay, so of course that becomes plus a positive. We add the two values together, keeping in mind sig figs. Remember, if you're adding values, it's based on the decimal place. And so that first value goes out 3 decimal places, the second one goes out 4, and so 3 decimal places is the shortest, and so that's what we'll use. And you get a positive 0.2905 volts. Okay, so remember I'm subscripting that last number because it's not significant, but I do want to keep one extra digit until I'm done with all my calculations. And so that is the standard cell potential. Right, and now that we know what the standard cell potential is, we can plug it into our equation that relates the delta G with that standard cell potential. And so the standard free energy change, delta G, is equal to negative N times F times that E cell value that we just found, that standard cell potential. Okay, so we're going to have to determine what is N, and that is based on looking back at your two half reactions that we have written here. Okay, so let's see, I'll just rewrite those out real quick. We've got the 2 copper 2+ ion becoming 2 copper with a positive charge, and we've got the tin neutral being oxidized to a tin 2+. And so we need to add electrons to get those charges to balance, right? If we were trying to add the two half reactions together, and we see that we've got that 2 positive charge. And so if we add 2 electrons to this side, then 2 positive, 2 negative will cancel out. That will give you neutral to compare to the reactant side of that reaction. And you can do the math, but you'll see that you also have to add 2 electrons to that top reaction, right? Because you've got an overall 4+ charge here and an overall 2+ charge here. And so you need to reduce that 4+ by 2 electrons. And so the 2 electrons in the balancing of those two half reactions, that is your value for N. Okay, so that's how you determine N, is by having those two half reactions balanced with the same number of electrons on opposite sides. Okay, so now that we know the value of N and the standard cell potential, we can simply plug this into the equation, and you get delta G standard equals negative N, which is equal to 2. And that is infinite sig figs. Okay, that's a whole counting number. And then times that Faraday's constant, which is the 96,500, and that is in units of coulombs per mole. And then multiply that by the standard cell potential that we calculated of 0.2905. And that is in volts. Now it's kind of hard to cancel out the volts and the coulombs unless you know that a volt is technically joules per coulomb. So if you go back in past discussions on this topic, you'll find that the definition of a volt is a joule per coulomb, and then that way your coulombs, those can cancel out. So you should get back joules per mole for your delta G, which you're used to seeing. And number of significant figures, of course, we've got 3 significant figures here and 3 significant figures here as well. So we should have 3 sig figs in our answer. And delta G standard, we get negative 56,066 joules per mole. But delta G values tend to be reported in kilojoules per mole, so you might need to convert this into kilojoules. So of course you're going to take that value and divide by 1,000, right, to get this into kilojoules, and so you'll move that decimal place over, and that would give you negative 56.1 kilojoules per mole. Okay, so we have found the standard free energy change, and then they also want us to find the equilibrium constant. So I think that it is easiest to use the equation that you have for the relation between Gibbs free energy and the equilibrium constant. It's just an easier equation, and so we get delta G is equal to negative RT times the natural log of K. And of course we can rearrange this equation so that the natural log of K is equal to your standard Gibbs free energy divided by negative RT. And so we can plug in those values. Of course, delta G, we want to probably put that back into the joules, because our R value, of course, is in joules per mole Kelvin. So you're either going to have to change the R value to match the kilojoules, or you could just use the 56,066 joules that we started with for that delta G value. And divide that by, that should be negative, right? And so divide that by negative R, which is the 8.314 joules per mole Kelvin, times the temperature in Kelvin, and this is at room temperature. So remember that room temperature is 25 degrees Celsius. Okay, and of course if we want that in Kelvin, we need to add that 273 to give you 298 Kelvin. 298 Kelvin at room temperature. Okay, and hopefully all of the Gibbs free energy should be joules per mole. So all of those units should cancel out, and we want that to happen because K, of course, is unitless. And solving that piece, you should get that it's roughly 22.63. And looking at significant figures, again, remember that we only had 3 significant figures from that 56.1, right? So that was 56,066, where the last 2 sixes were not significant. Okay, so 3 significant figures so far, and then we're going to look at how to solve for that natural log of k equals 22.63. So of course we need to take everything and raise it to the power e in order to get that natural log to cancel out. And then if you're looking at significant figures, when you raise something to the power of either base 10 or an e base, remember that the number of significant figures is just based on the decimal place right inside of that value, and so you really should only get one value back for k. And so k to one significant figure would be equal to 7 times 10 raised to the 9th power. Okay, so most of this is plug and chug, except that you do have to know how to take a reaction, right, separate it out into its 2 half reactions, determine which half reaction is the reduction and which is oxidation, knowing that it has to be the cathode minus the anode, so reduction minus oxidation. So you have to know all of that to calculate the standard cell potential. You also have to be able to determine the number of electrons by balancing those 2 half reactions, and so that gives you your value of N. And then once you have your standard cell potential and your value of N, you can basically plug it into the equation. And then the other trick there, of course, is just making sure that the units cancel out. And so the big thing is making sure that the delta G value is in joules before you go plugging it into the equation where you're using the R constant, right? So just remembering that R will always be in joules. And then, of course, watching all of your sig figs. So the next topic we're going to look at is the Nernst equation. So everything we've looked at so far, of course, is in standard state conditions. We know that because of that degree symbol next to each variable, right? The E standard and the delta G standard. So the Nernst equation gives us the ability to look at the potential of a redox system that is in its non-standard conditions. And so the way we relate this is to use the reaction quotient Q. And so remember, the equation to calculate Q should look exactly the same as your equilibrium constant equation, except that the concentrations won't be at equilibrium. So just remember, Q and K have the same equation, it's just that Q is not at equilibrium. And at room temperature, so if we're at 298 Kelvin, which we often are, there is a convenient way to write the Nernst equation where we combine the gas law constant, the temperature at 298 Kelvin, and Faraday's constant, and then we relate that from natural log to the logarithm equation, and so we get this simplified value where all we have to know is the moles of the electrons N and the reaction quotient Q, which means that we will have to know the concentrations of the reactants and the products. And then real quick, before we dive into some examples using the Nernst equation, you just need to have a basic definition of electrolysis. So you can go in your textbook and read a whole section in depth on electrolysis. But for this class, you just need to know that electrolytic cells are going to be the opposite of galvanic cells, right? So galvanic cells are where spontaneous redox reactions occur, and electrolytic cells are going to be where non-spontaneous reactions occur. And so you've got to have an external circuit that does work on the redox system in order to have that non-spontaneous reaction occur. And also keep in mind that galvanic cells, right, when you're looking at those cell potential values, you notice that those are always positive. Well, in an electrolytic cell, your cell potentials should be negative, right? Because again, non-spontaneous should give you a negative cell potential value. Okay, so now we're just going to look at some examples using the Nernst equation. So for the cell schematic below, we're going to identify the values for N and Q, so your reaction quotient and of course your number of moles of electrons, and calculate the cell potential E cell. All right. So first step here is that if we want to calculate the value of N, the moles of electrons, then we are going to have to split up this reaction into two half cells and then balance those, right? So this goes back to balancing an acidic solution. So when we write out that first half cell, right, we've got aluminum as a solid, and I'm going to ignore the states for a moment. But a neutral aluminum will react to form aluminum with a 3+ charge. And remember that if we're looking at the single vertical lines here, right, on the left side is going to be your reactant, and then it goes towards the product. And so our second half cell reaction, we've got copper 2+ as a reactant going to copper solid as your product. And so we've got copper 2+ charge going to copper that is neutral. And so we've got to figure out, of course, what is being oxidized, what is being reduced. I think that will be helpful in the long run. And which one is being reduced, right? That's the first one to look for. And you've got that copper 2+ going to a neutral. That charge is being reduced in that second reaction. And then that means that the first reaction with aluminum, that is being oxidized. You also know this from the cell schematic, right? Because the first reaction written is your anode, right? We always start with the anode and we end with the cathode in these cell schematics. And so of course the anode is where oxidation is occurring and the cathode is where reduction is occurring. Okay, so we've got our two half reactions. Of course we would want to balance the elements, but we can see we've only got one of each. Balance the hydrogens and the oxygens in that order. And we don't have hydrogens or oxygens in these equations. So we go on to balancing the electrons, and we've got a 3+ charge. That means we need to add 3 electrons, and then in copper 2+, so we've got to add 2 electrons to the side with the copper 2+. And those electrons don't match, and so of course we're going to have to multiply by a factor in order to get the number of electrons on either side to match. And so that top reaction we're going to have to multiply by 2, and then the bottom reaction multiply by 3. And so rewriting the coefficients for each of these, we get 2 aluminums, 2 aluminum 3+, and that gives us 6 electrons. And 6 electrons here, 3 copper 2+, and 3 coppers. So that means that our value for N has to be the number of electrons that, as long as they match on both sides. And so from that equation we learn that N is equal to 6. Okay, so we found our value for N. Our next step is to find the reaction quotient. So we need to add the two reactions together in order to figure out the reaction quotient. And so the 6 electrons will cancel on either side, and we are left with 2 aluminum plus 3 copper 2+ ions yields the 2 aluminum ions plus 3 copper. And we do want to include the phases at the end of a reaction. So aluminum is a solid, copper ion is aqueous, aluminum ion is also aqueous, and copper is a solid. And the reason that that's important is because remember, when we are calculating the reaction quotient or equilibrium constants, the only thing we care about are aqueous and gases. We ignore the solids and the liquids, right? So we can ignore the aluminum solid as well as the copper solid when we are calculating that value of Q. And Q will always be products over reactants raised to the power based on that coefficient. So on the product side, we have the 2 aluminum ions, and so we've got the aluminum 3+ ion concentration raised to the power of 2 from that coefficient. And on the bottom, we've got the copper 2+ ion raised to the 3rd power, again based on that coefficient. And we can plug in the values that were given from the cell schematic. They tell us that aluminum has a 0.15 molar concentration and that copper has a 0.025 concentration. And plugging those values in for Q, we get aluminum would be the 0.15 raised to the 2nd power divided by that for copper, which is the 0.025 raised to the 3rd power. And of course 2 sig figs there for both, and so we want to get 2 sig figs in our answer. That gives us 1,440. Into 2 significant figures, that would be about 1,400. Okay, and I can rewrite the 1440, of course, with subscripting that 40 because we'll need that Q value when we calculate the cell potential, which is the last step. So we've got our value of Q at about 1400. We've got our value for N at 6, and now we need to calculate the cell potential. So the equation for the cell potential E cell equals the standard cell potential minus, and because we are at room temperature, and if they don't tell us the temperature, we assume that we're at room temperature. And so we're going to use that convenient Nernst equation where you've got the 0.0592 volts divided by your value of N, and then times the log of your reaction quotient Q. Okay, and now we can plug in, we could plug in the value of Q and N, but we need to figure out what that standard cell potential is. And so to find that standard cell potential, of course, we need to do the equation where we've got E standard is equal to the cathode minus the cell potential of the anode. Okay, and we've determined that already, right? We said that the copper ion was where the cathode was occurring, so the copper plate is the cathode, and then your aluminum plate is your anode. So we're going to take the cathode, which is copper, minus the aluminum as your anode. So find the copper, and we are going from copper 2+ to a neutral copper, and so we need that second equation here. Second equation of the 2 copper equations. And then aluminum 3+, there's only one of those. Okay, and copper, remember, was your cathode, and aluminum your anode. And again, quick, easy way to tell that is because the anode is written first in your cell schematic here. Okay, and so cathode is the 0.34 minus the cell potential of the anode, which is a negative 1.662. And so again, subtracting a negative becomes adding the two together. And based on significant figures, decimal places, that goes out 2 decimal places. And so our answer should go out 2 decimal places, and we get 2.00, subscript that 2 because it's not significant in volts. So 2.00 volts. Now we can plug everything into our equation. We know that the standard cell potential is 2.002 subscript volts minus the 0.0592 divided by our N value that we found earlier. And remember, N is equal to 6. So divided by 6, and then times the log of that Q value, and we will use the 1440. Okay, so if you take the log of 1440, you're going to find that that is 3.158. And remember, 2 significant figures plugged into a logarithm will give you 2 decimal places out in your answer. So we've got the 3.158, which gives you the value from the logarithm, and then times everything else there. So you've got 3 significant figures in any of those numbers that you're working with. Okay, so we get back, simplifying this, we've got the 2.002 volts minus 0.03116. And based on significant figures here, the first number goes out 2 decimal places, the second one goes out 4 decimal places, and so our answer should only go out 2 decimal places. And subtracting those 2 values, we get an E cell of positive 1.97 volts. Okay, and of course, because that is positive, it is spontaneous. Okay, we're going to do one last set of examples. This is all building on the same question. So this question is asking us to determine the chloride ion concentration in a water sample at room temperature, and so we can use that convenient Nernst equation when we need it, using a galvanic cell constructed with a graphite electrode and a half cell of, and we've got this silver chloride reaction happening, and a copper electrode with 0.5 molar of the copper 2 ions as the second half cell. The measured cell potential when the water sample was placed into the silver side of the cell was 0.0925 volts. So the first question is asking, what is the standard cell potential for this cell in volts? And so they are asking, what is that E standard? And we know that that is equal to the potential of the cathode minus the potential of the anode. Okay, and so just to simplify this a little bit, I'm going to rewrite it here and focus in on what's important. So if we want to figure out what is the cathode and what is the anode, the best way to do this is to look at the fact that it's a galvanic cell. And so if it's a galvanic cell, we know that the standard cell potential has to be a positive value, right? Because standard cell potentials that are positive are spontaneous, and galvanic cells are spontaneous reactions. So we could subtract this either way, and we'll find that there's only one way that we get a positive value. You have to take the larger value and subtract the smaller. And so with the 0.337 being the larger value, that means that E cell is going to be 0.337 volts minus the 0.2223 volts. Okay, and you have to do that in order to figure out which one to subtract, because you can't just look at the two half reactions the way that they're written, because the way that they're written, of course, they're both reduction reactions, and so you've got the electrons written on the reactant side, and so that doesn't help you determine which is your cathode and which is your anode. And so the larger one, the one that we're starting with, that has to be the cathode, which forces the silver chloride part to be your anode. Okay, so standard cell potential, when we subtract those two values and based on significant figures, we want to go out 3 decimal places, then you should get 0.1147 volts, or rounded, that would be 0.115 volts. Okay, the next question is asking us to write the balanced equation for the overall reaction in acidic solution. Okay, so we are going to take the two half reactions that we've got, and we already determined that the cathode was the copper and the anode was the silver. And so we're going to have to flip the reaction for the anode, right? Because that's where oxidation is occurring. And so if we want it to be written as an oxidation reaction, then we're going to have to flip it where we've got silver solid plus your chloride ions yields your silver chloride solid plus an electron. Okay, again, so that you have an oxidation reaction. And then you have your second reaction, which is the copper 2+ ion plus 2 electrons yields that copper solid. Now, if I'm trying to balance, of course, make sure all the elements are balanced, which they are, and of course check for hydrogen and oxygen, which we don't have either of those. And so now we look at the electrons and we notice that the electrons are not the same number on opposite sides there. So we've got to multiply that first reaction by 2. And so we can throw a 2 in front of everything in order to get those 2 electrons to cancel out. And so just remember from doing this that N equals 2 electrons. Okay. And so rewriting this reaction with everything else, we've got the 2 silver, which is your anode, plus the 2 chloride ions, plus your copper ion, react to give you the 2 silver chloride plus your copper solid. Okay, so that's the overall reaction. And then our last step is to finally calculate the concentration of the chloride ions in the solution. And so that was the whole purpose of this. If we went back to the beginning, remember, a student wishes to determine the chloride ion concentration. So in order to determine the chloride ion concentration, we need to use that E cell equation, the Nernst equation, and because we are at room temperature, right, they told us 25 degrees Celsius, which is 298 Kelvin, then we can use the convenient Nernst equation, where we've got E cell, and actually let me go ahead to the next slide here and write this down. So we've got the E cell equals the standard cell potential minus your 0.0592 volts divided by N and times the log of your reaction quotient Q. So the reason why I changed from the first way that this is written is because I want to write in, instead of using those two half reactions, I'm going to write out that balanced chemical equation or balanced redox reaction that we figured out. Okay, so I'm taking those two half reactions that was given in the problem and rewriting it so that we have that entire redox reaction. 2 silver solid plus the copper 2+ ion plus the 2 chloride ions. Okay, and that yields the 2 silver chloride plus the copper solid. And the reason why I'm doing this is because eventually I'm going to have to use the reaction quotient, and I've got to put in that equation for the reaction quotient, and that comes from knowing the entire redox reaction so that we can do products over reactants raised to the power of those coefficients. And so that's why I needed to rewrite those two half reactions as the entire redox reaction. So we've already calculated the standard cell potential from one of the previous steps. Remember, that was the 0.115 or 0.1147. So we know that the standard cell is the 0.1147 volts. And then they tell us in the question, they tell us that the measured cell potential, right, and if they're measuring a value, that is E cell. Okay, that's your non-standard conditions. And so E cell is equal to 0.0925 volts. So we've got the cell potential at non-standard conditions, we've got the standard cell potential, and of course we calculated N whenever we did the two half reactions added together. Remember, we said that N was equal to 2 from your 2 electrons on either side. Okay, so we also know that that's negative 0.0592 volts divided by 2 and then log of Q. Okay, so let's first go about figuring out what the value of Q is, and then we can figure out the equation for Q and solve for those chloride ions. So our first step, of course, is to rearrange this. I would switch this entire section here and swap that out for the 0.0925 so that I can subtract the two values. So I get the 0.0592 divided by 2 times the log of Q equals 0.1147 minus the 0.0925. And all of those are in volts. And significant figures, 3 decimal places out. This one's 4 decimal places out, so we want to only go 3 decimal places out and carry that extra digit. And so the difference between those two, we should get 0.022, 3 decimal places out, and then you've got an extra 2 hanging there, and again in volts. So now that we've got that value, of course we can take this and move it over by flipping it, and so you would multiply by 2 and divide by that 0.0592 volts. And that's equal to the log of Q. Okay, multiply all that out and you should get back, and I'll rewrite it on a new page here. We get that the log of Q is equal to 0.75. And two significant figures, because you've got the two significant figures here, and when you put that in the calculator it just comes out to be 0.75. You don't have any extra digits to keep. So log of Q, of course, if we want to undo that, we're going to raise it to the power of 10. So raise both sides to the power of 10, gets the log and that to cancel out. So Q equals, and then based on significant figures, if we're raising 10 to the power of that value, then that value should get back two significant figures, and so we get Q equals 5.62, keeping an extra digit. And now that we know what Q is equal to as a numerical value, we can write Q as an expression of products over reactants. And so just going back for a second here, looking at that entire reaction, on the product side we've got nothing but solids, and so those solids, remember, those aren't included in your Q, your reaction quotient expression. So all those solids cancel, and the only thing we've got are those two reactants, the copper 2+ ion and the 2 chloride ions. And so when you don't have any products, remember, you're going to do 1 divided by those reactants. And so writing that expression for Q here real quick while we've got the reaction, Q is going to be equal to 1 over the concentration of the copper 2 ions times the concentration of those chloride ions raised to the second power. Okay, so let's go back. We've got Q equals 5.62, so we know that that is equal to 1 over the concentration of the copper ions times the concentration of those chloride ions raised to the second power. And they give us the concentration of the copper 2+ ions in the question. So it's a 0.5 molar concentration. And we can, of course, bring that over and manipulate. We get the 5.62 times that copper ion concentration of 0.500, and then, of course, times the chloride ion concentration raised to the second power equals 1. And rearranging this, we will get that the concentration of that chloride ion and squared, so we're going to have to take the square root of everything, would be 1 over 5.62 times the 0.5. And take the square root. So our concentration of those chloride ions, square root, and two significant figures based on that value of Q should get us back 0.60 molar for our final answer. Okay, so that wraps up our entire topic on electrochemistry. And that should be it for this section.